Alright, well in this video what we're going to do is we're going to take a look at the support reactions at a beam due to applied distributed loads. So in this case we might have a distributed load where the load is spread out evenly over an area, or it slopes. Maybe it starts at zero load on one side and goes all the way up to 1,000 pounds per foot in this case on the other side. So we can have different types of distributed loads. One's linearly varying, one's uniform, right? An example of a uniform load might be snow, where snow falls everywhere, right? And you might get a blanket of snow 1 foot thick in some of the places that where I live, but where you are it might be a little bit different, but that's a type of distributed load. So what we're going to do here is we are going to draw our free body diagram. With particular regard, we're going to take a look at those distributed loads. Okay, and what we're going to do is we're going to show resultants and locations. Also, what we're going to do is we will then take a look at and we'll apply our equations of equilibrium. Okay, so to get started, we'll draw a free body diagram. When I draw a free body diagram, I like to include all the unknown forces that we have at the support reactions. So here we have AX, AY, BY. I like to include the known forces as well. So in this case, we have our distributed, uniform load. We also have our distributed uniformly varying load, right? So this point here and this point here are 1,000 pounds per foot. Sometimes I'll abbreviate that PLF. Okay, in addition, this point here goes all the way down to zero. So there's our uniform loads, or distributed loads I should say, and then we'll have some dimensions in here, 6 feet, 4 feet. I like to include a coordinate system that is my positive sign convention. Okay, so we have now this is our free body diagram. All right, and this gives us and it identifies the loads that we're going to be looking at. So the first thing that I said here is we're going to take a look at those distributed loads. So distributed loads really come in two types. One that we'll deal with here is a triangular load. So a triangular load looks like this. All right, and then the other kind that we're going to really look at are the rectangular loads. So the triangular loads and the rectangular loads act as types of loads, but in either case what we're going to end up with here is a height W, which is essentially, in this case we have 1,000 pounds per foot, and some length of it as well. So I'm just going to call that L. Okay, and what we're looking for with this is where is the center of mass of this thing, because the resultant or the weight of all that load is going to act right through the center of mass. So maybe you can picture it, maybe you can't, but if you were to hold one of these shapes up and balance it in just one point, where would you have to balance it? Well, the rectangle, this would be at a distance of L over 2. With a triangle, we're 2/3 L from the big side, or 1/3 L from the short side. Okay, so again, when you're working with triangles, you have to be careful with which way it is. But what I'm going to do is I'm going to label this resultant here RT. I'm going to label this resultant RR. Okay, so when we come down here, we're going to solve for RT, and RT, all it is the area of that triangle. So you've done this formula a ton of times. W times L. Here, W is the height of the load, L is the length of it. All right, and same thing with the RR. What we're going to have here is this is just going to be W times L. So the height of the load times the length of it. The weight of all this force is going to be the weight of the individual component times the length of all of it. All right, so that's where we're going to go. And now what we need to do is, after we have our free body diagram, after we have our loads, we need to go and calculate those resultant forces, and I like to show them right on my free body diagram. So I'm gonna take those resultant forces and throw them in on the free body diagram. So this is RT, and we also have RR. All right, and so we also want to know where those act from point A. Okay, we'll get there in a minute, but let's first just solve and come back and solve for RT and RR. So in this case, RT is just going to equal 1/2 W, which we said W, oftentimes W is used for these uniform loads. So W is going to be this uniform load. We're going to say that's 1,000 pounds per foot times the length of it, which is 6 feet. Okay, and when we do the math out, half of 1,500 times 6 feet is going to be 3,000 pounds. Similarly, when we come over here to RR, what we're going to say is, well, RR is going to equal W, which is 1,000 pounds per foot, times 4 feet, and our feet cancel out, and we're left with RR is 4,000 pounds. Okay, so this is good. We have two intermediate results here that we're going to use in our program or our problem here. So the thing that we do want to identify too is how far are these points from point A, because when we come down to applying our equations of equilibrium and our sum of moments in particular, we're going to apply the sum of moments about a point. I like to use point A when we have a simply supported beam like this. And so what we want to know is the distance from point A to those forces. So if we make a line here and make a straight line, what we're going to say is, we want this distance and we want this distance, the distance to those forces, because that'll be our moment arm from point A. So the first distance, what we end up with is kind of this 2/3 L situation where L is 6 feet. So we're going to say this is 2/3 L, 2/3 of 6 feet is going to be 4 feet. Okay. When we come over to RR though, RR is a little bit different because we have to get to the rectangle first. We have to come all the 6 feet over, and then we go half of the distance, right? So we go half of this 4 feet. So what's that? Half of 4 is 2. So we end up with 6 feet plus half of 4, which will be 2. So 6 feet plus 2 is 8 feet. Okay, so now that we have that, we can come back and apply our equations of equilibrium. So let's do that. Sum of the forces in the x direction equals 0. I always like to start with that one because a lot of times it's easy, and in this case we only have one force in the x direction, ax equals 0. So if your teacher ever asks you for a volunteer for that one. All right, and then I like to go to the sum of the moments. Sum of the moments is a little bit more challenging, but let's take a look at it. Sum of the moments about point A equals 0. So when we write that, what we're going to say is we're going to look for any forces that don't pass through point A and look at the distances of their lines of action. So in this case, what we can see here is we have a few different forces that all are going to cause moments about point A. So RT, RR, and BY all are going to cause moments about point A. So we can see RT has a moment arm here, RR has a moment arm here, BY has a moment arm here. Okay, so we're going to take a look at that, and we're going to just back this up for a second and come down here and apply our sum of moments equation. So let's start. We're going to say RT times, well, we already told it, or we already figured it out, is going to be 4 feet. We know RR times 8 feet, and we have BY times, well, 6 plus 4 is 10 feet. All that has to equal 0, and now we need some operators. Which way are these moments going, or which way are these rotations going? So RT, hopefully you can see it, but it's causing a rotation in this direction. That's opposite of what our positive sign convention is, so we know that that one's going to be negative. Okay, RR is very similar, right? Same direction about point A, same opposite of our positive sign convention, so that one's also going to be negative. Right, and then BY is going the opposite way of these, so we're going to say that's positive. So now we get to substitute in. So minus RT, which was 3,000 pounds, times 4 feet, minus RR, which is 4,000 pounds, times 8 feet, plus BY times 10 feet equals 0. So if we take the two negatives, add those both to the other side, what we're going to get is BY equals, what we end up with is, I think 44,000 pound-feet divided by 10 feet, which works out to 4,400 pounds. So, if you're not getting that, check, feel free to stop, pause the video, take your calculator out. It's good calculator practice, and see if it works. Okay, but this is kind of cool because now we have a value, and we get a positive value. It means our arrow is assumed in the right direction. We're good. So we've got 2 of them done, and let's do the last one here. So the last one, what we're going to do is, let me start that over here. What we're going to do is we're just going to do some of the forces in the y direction. So oftentimes what I'll do is I'll say which way we're assuming is positive. So here we take all the forces that are vertical. So I'm just going to go left to right. So AY minus RT minus RR plus BY equals 0. So AY is going up, so I say it's plus, RT is going down, opposite of our positive sign convention, RR is down, opposite of our positive sign convention. BY is up. And now we can just plug in. So here we have AY minus 3,000 pounds, minus 4,000 pounds, minus 4,400 pounds. All has to equal 0. So when we're all done, oops, I missed it. This is a plus. So hopefully you caught my mistake. But here we go. We get AY. When we add all this up and figure it out, we get AY is going to equal 2,600 pounds. And real quick, one of the things that I like to do is just use a little bit of mental math here and say, well, 2,600 plus 4,400. Does that equal, AY and BY? Does that equal RT and RR? All the forces up equal all the forces down. Well, when we add 2,600 and 4,400, it does. So hopefully this example is helpful. If it is, definitely check out other videos. Hopefully I can keep helping you. So until next time, keep working hard and looking onwards and upwards.